All right, now that we know we have the algebraic background, we know what a group is, what a generator is, now we can easily define the discrete logarithm problem. So let G be a group and the small g its generator. Given A, it is feasible to compute G to the A. And given the output B, which is actually the 8th power of G, it should not computational feasible to find A. So this is the discrete logarithm problem. So you have the generator. When I give you A, you can add this generator to itself or multiply in this notation to itself A many times and obtain the result. But when I give you the output and ask you which power of G it is, it should be hard for you to find. Okay, this is how we define the discrete logarithm problem. But the most important thing is that the hardness, or more technical term, interactability of the discrete logarithm problem actually depends on the group G. Okay, so this is why we'll be talking about elliptic curves, because points on an elliptic curve will define a group, and there this problem will be harder, and we will call it an elliptic curve discrete logarithm problem. Okay, so let's talk about the logarithms and see why in some cases it is very easy and in some cases it is very hard. So let's start with infinite groups. So in this case, actually the definition will be logarithm problem, not the discrete logarithm problem, but just let's see why the logarithm is easy in some scenarios and hard in some other scenarios. So let's start with rational numbers and let's choose the group operation as addition. Okay. So given B and G, find A such that A times G equals to B. So in the previous definition, I actually used the multiplicative notation. If you give the same definition but use the additive notation, then here I will write A times G, and here B would equal to A times G. Okay. So let's start with this additive notation. So you are given B. You also know the generator G. I'm asking you what is A, so that A times G equals to B. So this is not a hard problem. It is easy to solve because if you divide both sides by G, this would mean that A equals to B over G, which is just a simple division operation, right? Consider also real numbers with multiplication this time. Okay, given B and G, find A such that 8th power of G equals to B. So question is this a hard question or is it an easy question? The answer is actually easy. So this is easy to solve. Calculate the logarithm of B to the base G. Okay, if you do it, this would mean that logarithm to the base G, here B would equal to the G to the A. Recall that any logarithm base and the value, if it is the same, then this will result with, A is sending to the here and the result will be 1. So it is just, simply calculating a logarithm. So you know B, you know G. Just calculate the logarithm of B to the base G and you end up with A. Okay. So this is actually the definition of logarithm, and this is why we call it a logarithm problem. Okay. Now consider ZP, but this time addition. Given B and G, find A such that A times G is equivalent to B modulo P. Question is this a hard or easy question? So one way you can do it, take G and multiply it with any number starting from 1 and check if it is B modulo P. But this kind of brute force attack would be, exponential time complexity, because if you choose P very, very large, then such a brute force attack will take a lot of time. But there's an easier way to solve it. Multiply B by G inverse. Thus, G inverse B would actually mean G inverse times A times G, because B is A times G modulo P. G's will cancel each other, and you will end up with A. So all you need to do is to compute the inverse of G. Okay, with respect to multiplication, of course. And question is it an easy thing to find the inverse of an element? We have the extended Euclidean algorithm, which finds the inverses in a very fast way. So as you can see, this discrete logarithm problem is very easy to solve once this operation is addition. And here, yeah, the same thing I mentioned. G inverse can be easily computed by using the extended Euclidean algorithm. As you can see, the security depends on the group. But if I change this addition to multiplication, then things will be harder. Okay, consider ZP and multiplication. Actually, here we should say ZP star. Given B and G, find A such that G to the A is equivalent to B modulo P. As you can see now, when we had the real numbers here, we didn't have modulo P. So we would simply calculate the logarithm of B to the base G, right? But now I'm working on ZP, so there's modulo P here. So every result is actually masked by the modular P operation. This is why, I cannot simply calculate the logarithm of P or anything. So best known algorithms to solve this problem are sub-exponential with respect to P. This is why we can use it in our securities, okay? We don't have a polynomial time algorithm to solve this problem. The previous ones here can be solved in polynomial time. Some of them actually in constant time. So here's an example. In my computer, I calculated in a very fast way. So I choose to generate a number 3, a small number. I choose an x value. I calculated the x power of 3 modulo this number and obtain this value. Question is, can you find x? As you can see, looking at these numbers, you don't have a direct idea what x is. I mean, in the worst case scenario, you can perform a brute force attack, taking, first power of 3, then the second power, third power, and so on, and check if it is this number modulo this. Again, this will be exponential time, but we have, as I said before, we have some sub-exponential time algorithms. So in this case, the x was this. And actually, you might think that, calculating a huge power of a number might be also time consuming for a computer. But since we are actually reducing the output with this modulus number, we are actually performing not a power exponentiation operation, but we are actually doing modular exponentiation, which is very fast. We have very fast implementations for that. All right. So next week we will talk about elliptic curves, but elliptic curve discrete logarithm problem is somewhat different. In this scenario, you are given an elliptic curve E defined over a finite field FQ, and you have a point P on this elliptic curve of order n, and the point Q, which is just the addition of this point to itself d many times. So question is, this point, this point, find d. Of course, now the question is, how do I add a point to itself? So, and why it is a group. We will talk about it next week, okay? But this elliptic curve discrete logarithm problem is harder than this one because we don't have any sub-exponential time algorithm to solve this, okay? This is why in encryption algorithms, your secret key is reduced if you use elliptic curves, okay? That is the whole idea. Okay, so let's see the security and let's talk about group sizes. There is a polar draw algorithm that can solve the discrete logarithm problem in about, square root of q over 2 complexity. Here, you can think this as a big O notation. Index calculus algorithm can solve discrete logarithm problem on ZP with sub-exponential time complexity. This one is, exponential time. Index calculus algorithm uses relations between small primes, which is not applicable to elliptic curve discrete logarithm problem. Thus, using elliptic curves allows us to work on groups with smaller number of elements. Okay, this is the idea. And maybe I have a slide about it. So before talking about, yes, here. Before talking about Diffie-Hellman key exchange, let me talk about the security here. Recall that in symmetric key cryptography, we said that the secret key shouldn't be smaller than 128 bits, because nowadays this is what we call personal security. This is what we call military grade security. So if you use AES with the secret key of size 128 bits, then your security would be, considered secure in 2016 to 2030 and beyond. So if you want this level of strength, 128-bit security, then your discrete logarithm group size should be 3072 bits. Okay. We haven't talked about RSA yet, but their RSA factoring module should also 3072 bits. This is the number which was the multiplication of two primes. But as you can see, your elliptic curve secret key can be as small as 256 bits. So we can work on the groups of this size, fields of this size compared to this. This is the advantage of elliptic curves. This is why you hear things like elliptic curve cryptography. But of course, in this case, when we work on ZP star, we are actually performing regular addition and multiplication operations. Here we are doing elliptic curve arithmetic, which is more constant than these simple operations. Okay, so let's go back. All right. So let's talk about now Diffie-Hellman key exchange, how we can actually securely exchange secret keys over the internet, which is considered as an insecure channel, communication channel. So A and B wants to communicate. In crypto, generally, we refer them as Alice and Bob. So they want to exchange a secret key. Probably, for instance, they want to use AES. So they want to agree on a 128-bit secret key, which nobody knows, okay? They can do the following. A picks a random number, small a, calculates G to the A, and sends it to B. B also picks a random number B, calculates G to the B, and sends it to A. Now, A computes the 8th power of the number it received, okay, which turns out to be G to the power AB. B also computes the bit power of the number A sent to him, and both of them now becomes equal. Okay, so this way now they agreed on something which they didn't know beforehand, and they calculated in a kind of a secret way. So in order to visualize this, let's focus on the ZP star scenario, where I choose the R group as the multiplicative group modulo P. And here Alice and Bob wants to communicate. So we have the group G, which is actually, ZP in our scenario. And small g is its generator, okay? So these are public parameters. The group is known, its generator is known, and P is known. P actually is modulo P number, okay? So the communication turns out to be this. Alice randomly chooses small a, which is a value less than P minus 2, okay? Calculates the 8th power of G modulo P, and let's represent it with capital A, and send this value to Bob. Bob randomly chooses a number B, calculates G to the B modulo P, and sends this value to Alice. So Alice takes the 8th power of the number it receives, and Bob calculates the bit power of the number it received from Alice, and both of them turns out to be the same, right? So now this is probably a huge number, like maybe 10,000 bits, doesn't matter. You can say that, okay, let's choose the leftmost 256 bits as our AES 256-bit key. From this point on, you can communicate using AES. So this is, assume that this is the internet, and we use this insecure channel. And Alice and Bob didn't communicate it before, didn't agree on a secret key before. Now with this exchange, they agreed on a secret key. Question is why it is secure? Because The person who is listening to the communication knows these public parameters like G and P. By listening to the communication, they also captured A and B. Recall that A is this and B is this. Let's focus on only one of them. So the attacker captured A. So A is actually G to the A modulo P. Attacker knows G, attacker also knows P. Now the question is, can you find the small a from these three values? So this is actually the discrete logarithm problem, right? So if you can solve this in a very fast way, then you can capture small a. If you capture small a, then the attacker, captured the secret key because they also know the B and they captured the small a. By taking the a power of B, they also calculate the secret value. So this way, they also capture the secret key. Okay, the whole actually security here depends on the hardness or interactability of the discrete logarithm problem. So if you can come up with a faster way of solving this problem, then you can break the internet actually. So this is why we are actually talking about post-quantum cryptography, because this problem can be solved in polynomial time if you have a very, very huge quantum computer. Okay, this is the main problem about technology. So with our current technology, this problem is hard because if you somehow build many, many faster computers, we can simply increase the value of P and have security. But if somebody can build a very huge quantum computer, then this problem is easy to solve. Okay, so this is why we are trying to come up with key exchange or encryption, public key encryption algorithms which are quantum secure. So those algorithms would rely on a problem that is different than discrete logarithm problem or integer factorization problem, which will be harder for quantum computers to solve. Okay, but this is the picture. This is the thing that you should know about Diffie-Hellman. As you can see, this way anybody on the internet can agree on a secret key without communicating personally or physically, in a secure channel. So let me give another example. This time, I will talk about El-Gamal encryption scheme. So we can use discrete logarithm problem to create an encryption algorithm. So this is not an encryption algorithm. Diffie-Hellman key exchange is just a key exchange algorithm, right? We agree on a secret key. Let's design an encryption algorithm which relies on this discrete logarithm problem. So El-Gamal encryption scheme, I will briefly mention it on this slide. Key generation is very simple. You randomly choose a value x. This will be your secret key. Then you compute x power of the group generator G, calculate y. So this will be your public key. So it is as simple as that. You chose the private key x, calculate the x power of G, and obtain the public key y. So you give y to everybody, and when somebody wants to send you a message, M, they do the following. They choose random R. So they calculate the following two values. R power of G, also their message multiplied by R power of Y, which is your public key. Okay, they send you U and V. The encryption works like this. You receive this U and V and multiply V with U to the power minus X, where X is your private key. And we claim that this is equivalent to M. This is not that hard to see because think about U times V. U times V is just multiplication of these two values. But here I'm taking the minus X power of this. So there is a, minus X power here. Sorry, U to the power minus X. So you are simply multiplying G to the minus XR with this value. But Y to the R is actually G to the XR, right? So you are actually canceling this value with this one, so you end up with M. This is why El-Gamal encryption works. So anybody capturing U or V should have a way of, solving the discrete logarithm problem to capture R or, anything else. Or similarly, once you publicly share your public key Y, attacker knows this value Y. They also know the group generator G. So if they can solve the discrete logarithm problem, they can capture X. As you can see in this slide, I'm talking about the group generator. I'm not giving any specific group. So you can use El-Gamal encryption using elliptic curves. Okay, so your group can be elliptic curve here. So this is why in that scenario, your secret key X can be smaller or group size can be smaller. But if you're using the multiplicative group like ZP, then that P prime number should be at least 3072 bits long. Okay, so this way, let me recall our table again. These are the key lengths that are recommended, that we recommend. So this is the minimum line that I can recommend to you. Anything lower than this can be actually susceptible to broken. Maybe not maybe today, but maybe in a few years they can be broken. So this is why you shouldn't rely on this case. For instance, if you are using RSA 2048 bits, then maybe your security will not be that long. Maybe in a few years somebody can break it. You don't know the capacity of the secrecy agencies and the computational power. So this is why we always suggest that stay at this part. If you need military grade security, move on to this part. But as you can see, if you move on to this part, the group sizes becomes really large. Think about designing a hardware that works on groups of 15,000 bits. So designing such a hardware and the speed will be a problem. This is why most of the time people are using this. Okay, this is why we also suggest elliptic curves, because instead of working on group sizes like this or RSA modulus like this, you can just work on 512 bit values. This way, once the key sizes increases, elliptic curves becomes more advantageous.